Can plant foods and their phytochemicals be used to reduce arterial plaque?
This is a clip from a live Q&A session open to CMJ Masterpass members. In addition to this episode, you can access lots of other free samples from these sessions at the first link in the description.
The winner of this month's question contest is John Needham, whose question I would summarize as, can plant foods and their phytochemicals be used to reduce arterial plaque? Before I get to John's full question, I want to give a background of the mechanisms of atherosclerosis and how they inform how I would think about such a question. So I'm going to go to a paper that has some great figures. This paper is Role of Oxidized LDL in Atherosclerosis by Leva, Wenger, Guzman, and Orrego. And it's you can see the information there. I want to skip to a couple of figures that they have down here. So what's going on in the development of atherosclerosis, according to modern knowledge, is that lipoproteins in the bloodstream, with an emphasis on LDL particles, will travel in and out of the subendothelial space. And so the subendothelial space is this space behind the endothelium, and the endothelium is the innermost layer of cells of a blood vessel that is in contact with the lumen of the blood vessel. So the lumen is where the blood is flowing. It's the open space in the blood vessel for the blood. And then the blood vessel wall is composed of three main layers. The innermost layer is the endothelium, and the endothelium is, this is probably not exactly true, but is generally described as a single layer of cells. And there are gaps between the cells, and there is opportunity for things of various sizes to float in and out of those spaces, going in and out of the subendothelial space. And the subendothelial space, which is behind the endothelium, on the other, so this is the blood up here, not depicted. The subendothelial space is on the other side of the endothelium, and it is between the endothelium and the other layers of the blood vessel. And although it's not depicted here, these LDL particles are not just coming in and getting caught. They're coming in and they're going out, right? So if you added more detail to this picture, what you'd see is these LDL particles are coming in here, some are leaving over here, and they're just constantly going in, coming out. It's totally normal. There's nothing wrong with it. It's going to happen throughout your entire life. Now, inside the subendothelial space, you have a much more oxidative environment because of the types of enzymes that are produced over on this side of the blood, and due to the antioxidant balance and due to the constant surveillance and presence of immune cells in this place. And the LDL particle does not have to get caught on proteoglycans, which are these green structures here. But there are proteoglycans that can catch the LDL particle. And if they catch the LDL particle, they'll keep the LDL particle there for longer. Now, there are reactive oxygen species that can oxidize the LDL particle in here. And they can oxidize any LDL particle that's in here. And of course, LDL particles can also oxidize in the blood. So they don't have to get caught on the proteoglycans to oxidize, but if they do get caught on the proteoglycans, they will spend a longer period of time in the subendothelial space, thus a longer period of time exposed to the reactive oxygen species, and thus they will be more likely to exceed the threshold of their own antioxidant protection. So although not depicted in this picture, one of the things that has to happen during LDL oxidation is that if you just take an LDL particle in vitro and you expose it to oxidants and you just watch what happens, there's what's called the lag phase. And then all of a sudden you have this dramatic explosion of oxidation at some period of time afterwards. Why is that? It's because the LDL particle, often originating from VLDL particles that had left the liver, whichever there is LDL secreted from the liver, but there's generally most LDL in plasma is metabolized down from VLDL that was secreted from the liver. It doesn't really matter. The point is when lipoproteins leave the liver has packaged them with a bunch of stuff that includes antioxidants. And so if there's a little bit of contact with reactive oxygen species, it doesn't really matter, because all that happens is you lose a little bit of the antioxidants in the LDL particle. But if that LDL particle is exposed to enough oxidants for enough time, then a threshold will be crossed, and the first thing to oxidize will be the polyunsaturated fatty acids in the membrane of the LDL particle. Though the oxidation of PUFAs in the LDL membrane will eventually lead to the oxidation of the protein in the membrane, and the oxidation of the protein will change its interaction with receptors. So it will no longer be taken up by the LDL receptor if it were to encounter the liver, but it will be taken up by macrophages scavenger receptors, which plays an important role in atherosclerosis. Now, there is oxidation of the cholesterol in the LDL particle, and that's not irrelevant, but it's also not the main story going on. And so if you look at quantitatively what is present in oxidized LDL that does the most to stimulate the process of atherosclerosis, it's actually the oxidized or the products of PUFA oxidation, polyunsaturated fatty acid oxidation in the LDL membrane, that are driving the process the most. In any case, you also have immune cells called monocytes. And monocytes, their role is primarily surveillance. So they're circulating through the blood, they're circulating through the LDL, the subendothelial space. So they're doing the same thing that these LDL particles are doing, and everything else that fits between the endothelial cells, all of it is coming in and going out, coming in and going out all the time. But if these monocytes, now this picture is a little misleading. So this picture shows that the endothelial cells are secreting adhesion molecules and chemoattractants such as intracellular ICAM and VCAM. So intracellular adhesion molecule, vascular cellular adhesion molecule, and implying that this is what brings the monocytes over. There's truth to that, but actually the monocytes are always there. They're always coming into the subendothelial space. They're always leaving. However, more of them will come if there is an inflammatory process induced by the oxidized lipids to make the adhesion molecules and chemoattractants. Moreover, and more importantly, more of them will stay there. So one of the key events here is that, and this really isn't depicted in this picture, but if you have oxidized LDL in here, you will have these monocytes deciding to stay, and they will morph into resident macrophages. And that's basically saying the monocytes are surveilling. They're saying, is there anything to clean up? And then they found something to clean up. It was the oxidized LDL. And so they stay there in the subendothelial space, and they say, you know what, I'm going to be a bigger cell. I'm going to be a macrophage, and I'm going to just stand here and watch out for oxidized LDL because I've seen it here before, and I'm going to make sure it gets cleaned up. And over time, that leads us to things that are happening in the next figure. Okay, so they depict this process much better in this figure. So the monocytes come in the presence of oxidized LDL, they differentiate into macrophages. The macrophages specialize in taking up the oxidized LDL, and as they do so, they become like giant cleanup sites. And they turn into these foam cells, which is basically like, I'm just going to be a giant warehouse for all this gunk. Okay, now that's the process as we know it now. And if we go back to what was known back in, say, 1930 something, when Nikolai Anichkov wrote a absolutely fantastic English language review of all the Russian literature since the 1800s up to that point. One of the things that was known was that you could produce this process in a rabbit by feeding it cholesterol. But another thing that was known was that if you stopped feeding the rat cholesterol, it was totally reversible. And there's been nothing ever to contradict the principle that was learned from these animal experiments, that the only thing you need to do to reverse atherosclerosis is remove the cause. And if you remove the cause, it'll go away. Now, that might not be true if you have advanced atherosclerosis characterized by successive ruptures of the plaque and rehealing with scar tissue and clots that build up. All right, you may get to a point where there are certain sites that have advanced characteristics that are not totally reversible. But I'm not so sure, because even in an advanced plaque where you have successive rupture and rehealing and repeated instances of clotting, it's still the buildup of oxidized lipids in the area promoting inflammation that's degrading the collagen in the cap, that is overcoming the rate of collagen synthesis, thus causing a rupture. And so if you just remove the accumulation of the oxidized lipids, you should reverse even that process. And so you might not get the artery to look like a brand new artery, but you should be able to return an unstable plaque to a stable plaque. And stable plaques don't cause cardiovascular events. Stable plaques are not the cause of ischemic strokes, and they're not the cause of myocardial infarction. The only way that you can get a cardiovascular event from stable plaques is if they are so overwhelmingly enormous and obstructive in all three coronary arteries that you have a chronic reduction in the blood supply to the heart, and that's not the usual cause of a heart attack, and that's not the likely case at all in someone who's relatively health conscious. Okay, so that said, with that in mind, let's take a look at the studies that John was talking about. So John's full question is reducing the level of cholesterol buildup in the wall of arteries. This paper contains the statement in the introduction that cholesterol efflux, the initial step of reverse cholesterol transport, is known to enhance the export of excessive cholesterol from peripheral tissues, in particular macrophages, and thereby to inhibit the accumulation of cholesterol in the wall of the arteries. Later, it states that falcarinadiol is a typical constituent of roots and rhizomes of Apiaceae plants, I don't know if I'm pronouncing that correctly, used worldwide, including in Europe, such as commonly used vegetables and herbs, carrot, celery. My own research suggests parsley and coriander, cilantro in the US, are also members of this family. Then John says, this next paper, stated that in the control group that did not consume pomegranate juice, common carotid intima media thickness increased 9% during 1 year, whereas pomegranate juice consumption resulted in significant intima media thickness reduction up to 30% after 1 year. I understand the IMT, the intima media thickness, to represent the buildup of plaque in layman's terms. Question 1, what would Chris support? Would Chris support drinking smoothies with an emphasis on celery, parsley, and coriander and cilantro? Question number 2, would Chris support deliberately eating pomegranates? The sample size was small, but other studies also suggest beneficial effects. Question 3, does Chris have suggestions for other foods that may have an effect on reducing the IMT or indeed stopping buildup in the first place? All right, so in this paper is just totally kind of like focused on a very narrow mechanism. So they took this compound in carrots. This is the graphical abstract, summarizes what they did. And what they basically found is, we were talking a minute ago about macrophages taking up the lipoproteins. And so one of the paradigms of reversal of atherosclerosis is reverse cholesterol transport, where these macrophages not only have the receptors that take up the oxidized lipoproteins, but they also have means of removing cholesterol to HDL particles. Now, I think reverse cholesterol transport is true, although I think it also became a very narrow, overly narrow focus that really hasn't played out the way anyone wanted it to. So when it was discovered that there was differences in the associations between LDL and HDL with heart disease, people tried to explain it. And their first explanation was that the HDL can take the cholesterol out of the blood vessel wall in the way that's shown on the screen. However, if you look at the lipoprotein cycle, one of the things that HDL does is it passes that cholesterol onto LDL particles that then bring it into the liver. And so, one of the things that they've done with this hypothesis is come up with cholesterol ester transfer protein inhibitors as a means of pharmacologically increasing the HDL cholesterol content based on this hypothesis. And they haven't worked. So I think it's important to not get caught up in a narrow mechanism like this. Now, it's quite possible that if what this study is saying is true, is that carrots are more effective than these pharmacological inhibitors because they're not focused on keeping the cholesterol in the HDL. They're just focused on getting it into the HDL in the first place. But I don't really agree that this is so obviously central to the processes we were talking about before, because once you have a ton of oxidized lipids in the subendothelial space, you want them secured in the macrophages because they're toxic to the cells. And the key driver of the process is not the total cholesterol content in the macrophage. It's the total amount of oxidized lipids driving inflammatory gene transcription that then, in what you really care about if you have advanced atherosclerosis, is the plaque stability. And it's oxidized lipids driving inflammatory degradation of collagen that is relevant there. So all right. So you're getting robust activation of cholesterol export from the cell mediated by the apoprotein from HDL, and it's rivaling that of a drug. So one of the questions that you would want to get is like, how many carrots do you have to eat, or how much of this stuff do you have to pop to get your phelcarinadiol levels up to 20 micromolar? Pomegranate juice consumption for 3 years by patients with carotid artery stenosis reduces common carotid intima media thickness, blood pressure, and LDL oxidation, by Michael Avaram and colleagues. All right, so they randomized people to either their patient. Well, they started with 19 patients from their vascular surgery clinic, 5 women and 14 men, aged 65 to 75 years, non-smokers with asymptomatic severe carotid artery stenosis, defined as 70 to 90% stenosis in the internal carotid arteries. And they randomized the patients to either pomegranate juice or placebo. They don't state what the placebo was, and that's a little odd in the case of drinking pomegranate juice, because I would like to know, what fake pomegranate juice they gave and what constituents were in it, and what was the sugar content and all this stuff. So it's weird not to have an explanation of that. 10 patients got the pomegranate juice, 9 did not consume pomegranate juice and served as a control group. So the way they describe the results is sketchy. All right, so what you would expect, right, is take this graph of the primary endpoint here, carotid intima media thickness. You would expect to see the placebo group plotted against the treatment group. I mean, this is time after pomegranate juice consumption in the 10 patients who had the pomegranate juice for up to a year. And it's like you randomize them to a placebo and pomegranate juice. Where's the placebo group? So to find the placebo group, you have to go up here and you have to read it, and it says mean intima media thickness of the left and right common carotid arteries from severe carotid artery stenosis patients that did not consume pomegranate juice increased significantly by 9% during 1 year period, from 1.52 to 1.65. In contrast, mean IMT in the patients that consumed the pomegranate juice for up to a year was reduced after 3, 6, 9, and 12 months by 13, 22, 26, and 35% respectively in comparison to baseline values. Like in a randomized controlled trial, the primary endpoint, the primary statistical analysis should be the primary endpoint at the end of the trial in the treatment group versus the placebo group. And so you have to go to the paragraph to find the values for the placebo group, and you have to go to the graph to find the values for the treatment group. Why are they so adverse to putting them together? That's extremely weird. Now, one of the things that I look for in these percent change from baseline comparisons is the possibility that regression to the mean affected the results, because regression to the mean basically means if you have a randomly high value, chances are it's going to be lower later. If you have a randomly low value, chances are it's going to be randomly higher later. And this is just built from it's almost like a law of physics, although it's a probability effect rather than it's not a guaranteed effect, it's a probability effect that just results from the fact that if you find people with a higher than normal value, everyone's value varies up and down. And so chances are you caught some of those people when they were just randomly higher than their own mean value. Therefore, the overwhelming probability is those people are going to be closer to their mean value later. So one of the things I would want to look at is, did the placebo group and the pomegranate group have a similar or different baseline value? And the placebo group here had 1.52 millimeters for a baseline value, which is very similar to what they show in the graph and never state for the pomegranate group. Is that right? Yeah, that's right. So it's just over 1.5 here. So it excuse me, it doesn't look like there's a regression to the mean effect. It looks like there's a real effect. But the fact that their presentation of this data is so terrible makes me, not want to jump on the findings of this study. It's just it's a little sketchy. It's inappropriate, and I just, I have to be caught up with wondering, why did they not want to show us the placebo group's data here? My guess is that the placebo group's data was really noisy and that the differences were not statistically significant at any time point, and that it went up and down in a way that made it a messy story rather than a clean story. And so the fact that I'm reading into it, right? But in my mind, the fact that they had to remove the placebo group to show a clean story that had a graph that they liked means that this graph is misleadingly clean, right? So, overall, my opinion is basically go back to the original principle. All you have to do to reverse atherosclerosis is remove the causes of atherosclerosis. So I don't think being caught up in narrow mechanisms of reverse cholesterol transport is the right way to think about it. And part of this is I'm biased towards root cause thinking, right? And so I look at the process that we showed before and I say, what's going wrong here? It's not the primary problem in atherosclerosis is not that you have a deficiency of the stability of the export protein in the macrophages. The problem is that you have too much oxidation of lipids. And part of that is poor clearance of the LDL particles due to low thyroid signaling, due to genetics, due to whatever can slow the turnover of the LDL particles, anything that can contribute to a low metabolic rate. And you have a deficiency of the protective factors, and you have a deficiency of things that help regulate inflammation and things that control oxidative stress. And you have a deficiency of collagen synthesis being able to in the advanced stage, you have a deficiency of collagen synthesis, being able to keep up with the inflammatory degradation of the collagen. So I prefer to focus on those. And if I'm trying to say where do these plant compounds fit into that, then I think there are many thousands of such phytochemicals in plants that have a wide variety of independent effects that are very hard to tease apart. But they also have some effects in common, which is that they tend to be generally stimulatory towards antioxidant and xenobiotic defense because they are xenobiotics. Our bodies treats them as such, and our bodies responds to them in the same way that we respond to increased fitness from exercise. We respond to the wide variety of these plant compounds with improved fitness of antioxidant xenobiotic defense. And that will help play a role in protecting against the oxidative environment and the antioxidant depletion in the LDL particles that contributes to that process. Now, would I advocate specifically carrots and specifically pomegranates? No. Do I think pomegranates can be a great plant food? Sure. I've eaten pomegranates. I think they taste good. I think they're nutritious. I think their antioxidants are great. But my position on this remains what it is, the same way that we covered a couple of months ago when I believe you asked a similar question. And that's, if you eat a plant-inclusive diet designed to get your vitamins and minerals at their targets, that includes a wide variety of fruits, vegetables, herbs, and spices, then I think you have your bases covered with this. And if pomegranate fits into that, great. Or if you just like pomegranate, great. But I don't see any point whatsoever in using, low quality studies of people's pet phytochemical to list out specific targets for carrots, parsley, coriander, or pomegranate. So that's how I see that. Thank you, John, for your question. I hope that helped.
This is a clip from a live Q&A session open to CMJ Masterpass members. In addition to this episode, you can access lots of other free samples from these sessions at the first link in the description. If you want to become a Masterpass member so that you can participate in the next live Q&A, or so that you can have access to the complete recording and transcript of each Q&A session, you can join at chrismasterjohnphd.com/masterpass. You can save 10% off the subscription price for as long as you remain a member by signing up at chrismasterjohnphd.substack.com/Q&A. That's Q&A spelled out as Qanda. These links are in the description.